Well, welcome everybody. This is Dr. Michael Timms, and we're going to have a lecture on solubility. It's going to be broken into two parts, and this is part one. So why don't we jump in? We've got some new terms. Some of you are probably familiar with these, others may not be, but it's worth reviewing them. And I'll let you go ahead and if you need to stop this slide and look them over, you certainly can. I'm not going to give definitions for each, but really what we're doing is we're breaking the definitions into either what's solid or what's extracted in the liquid. Solubility is whether something actually dissolves, and this is like sugar in tea. If you think about tea being hot, you're going to be able to dissolve a lot more sugar versus cold. Some of that has to do with the energy of the water. And when we talk about constituents, what we're really talking about are the chemicals that make up the phytochemistry of that plant that's being extracted. And precipitate really is very similar in some sense. It's not really like the mark, but that would be when you take something like kava kava, which is much more soluble in the compounds, the kava lactones, in a high alcohol content tincture, and you put it into water or juice, and you begin to see a kind of a white material that sort of forms in the water. That's literally some of those compounds coming out of solution or precipitating. So anytime we do any kind of extraction process and we are discussing solubility, it's really about selectivity. Right? It's a rational choice, hopefully a rational choice, where we're looking to see what will dissolve something or potentially what will precipitate out something, selecting against. So when we review some of the phytochemical classes, we can see some generalizable behaviors in the kinds of solvents we're going to be using in our medicine making processes. So we're going to start with the glycosides, and this is a sugar, a glycon, and a aglycon, which is the parent molecule that the sugar hangs off of. And these are made by plants oftentimes because the sugar increases the solubility in a water environment, which cells are. And it's a way to protect the activity of that molecule inside of a cell. And these glycosides tend to be soluble in both water and alcohol. Generally speaking, 25% and up alcohol prevents hydrolysis of the sugars. And this is sometimes based on the fact that you have enzymes present in the plant that will cleave or cut that sugar away from the parent molecule. We're going to look at anthocyanins in some of our experiments later on in the trimester, but certainly you can think of a lot of glycosides out there. The products of ginseng, ginsenosides, are all glycosidic, and they can vary in terms of where they attach to the molecule, to how many are there, and they have different roles. So the anthocyanins, glycosides in elderberry, are actually absorbed and excreted with the sugar attached. The activity is associated with that. In ginseng, the ginsenosides, they actually need to be biotransformed by our gut bacteria and our enzymatic system before it becomes activated. So it's going to be different from plant to plant in terms of how you might handle it. We'll learn later on how a pH can affect the stability of some of these glycosides as well. So alkaloids, these are in the plant often in the form of a salt, meaning they will bind with a malic acid or might be something like a calcium, any number of compounds. And the reason for that is actually it increases the ability of the plant to store these in vacuoles. But most alkaloids have a limited solubility in water, and you can alter that by doing changing the pH. There's a whole extraction process called an acid-base shakeout, where you can select for different types of alkaloids based on the pH level. But alkaloids in general are soluble in alcohol and in glycerin. And we'll get to some of the differences between this water, alcohol, glycerin issue in a minute. Volatile oils, right, these are the ones that we would associate with what we can organoleptically detect in plants. These are soluble in glycerin and alcohol, 45% on up. They extract in hot water, but you may alter the compound. So some of these can be heat labile. So just because you can get more out using a certain process doesn't mean you're getting the parent molecule, that you haven't altered it. And oil extraction of these is actually limited. It's surprising that they don't extract better with the oils. Some of this has to do with, it's not just how they dissolve in a certain compound, but that compound has to penetrate into cell structures. Even when we grind the herbs, there's still cell structures left that need to be penetrated by that solvent to get in literally and dissolve and carry out stored chemistry in plant cells. So there's a whole series of compounds that tend to be harder to extract: gums, resins, tannins. And if you look at this carefully, you can see how you might differentiate between them. Gums are soluble in water and alcohol. They're insoluble in glycerin. Resins, they need high alcohol and heat. And this is one of those situations where you're not going to break down the compounds with heat. And tannins have varying solubility in water and glycerin. Very high when there is glycerin present with water, and heat and alcohol in this case will precipitate it. So think about this. Take a minute if you want to pause the video and think about how you would differentiate if you were trying to pull out one over another or precipitate one so that it wasn't in the liquid. So to give you an example, if we take bark and we look at what was removed in whole or part in the typical solvent system, and this first one you'll see there's ether or chloroform. We don't really use that as much anymore, but I'll come back and I'll give you an idea on some things that folks are trying in place of those. But if you go and look at the old eclectics, Kings or Felters, you're going to see extraction with chloroform. And this was often applied back in the day. Not in my day, I didn't exist back in the early 19th centuries, but in someone's day, right? So when we look at this, what we're really looking at are either pH changes, energetic changes, hot or cold, or we're looking at polarity differences. And I'll come back to this in a little bit more in a minute, but just to give you a sense of how we're differentiating, how we're making rational choices, so that ether chloroform is going to be a highly lipophilic, liking oil, liking lipids, and nonpolar. So here terpenes and their derivatives, fats, waxes, free fatty acids, alcohols, sterols, resins, as we saw in that past one, are going to be extracted with chloroform. In alcohol or aqueous alcohol, hydroalcohol, we're going to pull out the polyphenols and their glycosides, tannins, mono and disaccharides. If we apply hot water, we're more likely to pull out starches and gums, pectins, mucilages. And you'll do some experiments with some mucilage later on in the trimester as well. And come back to this and think about hot versus cold water. If we look at aqueous alkali, or a basic water extraction, and we would tend to use something like baking soda in our setting here, but we would look at phenolic acids, some bark lignin and hemicellulose, suberin fragments, because when we are dealing with the bark, and I'll give a little bit more description of this in a lecture toward the end of the trimester when we look at green tea extraction. you're looking at cell walls, plant cell walls, and they are this amazing weave of long polymers such as cellulose cross-linked with hemicellulose and lignins and other types of compounds that literally create a framework, a rigid framework to actually act as a cell wall to provide structure to cells, and that's part of where we get trees' ability to grow to great distances is based on this structural integrity. So we're going to be pulling out lots of things that you might not see necessarily in an herbaceous herb or a root component or a flower. So just to keep that in mind, that not all extracts are going to have things like these pectins or suberins or hemicelluloses or lignins. In an acid hydrolysis, lyse meaning to cut, and an acid water, hydro, you're literally cutting it. You're really going to pull out simple sugars, uronic acids, things that would hang off of bigger molecules, and you're going to tend to leave behind the lignin. If you look back under the base extraction, it does tend to extract some of the bark lignins. So in the case of base, the lignins are driven into solution. In the case of more acidic conditions, it tends to precipitate out. So you can, through this acid-base shakeout, actually either pull into solution or drop out of solution. Now, just to give you an idea of alternatives to chloroform or N-hexane, these tend to be traditional benchtop, highly lipophilic solvents. And just to look at it for a couple, there's a lot of data here. But really look at these terpenes, these essential oils like d-limonene, pinene, cymene. These are things you would find in an essential oil extraction, and they can be isolated. But if you were going to use just some simple essential oils that you picked up, and you might want to fool around with diluting them in a olive oil or an alcohol, you could come up with an altered polarity to a solvent that might help if you ran into some issues getting something out of a plant that was highly lipophilic. Some of these measurements in terms of trying to figure out their properties, how alike they are, have to do with molecular formula, weight, density, their flash points, boiling points, viscosity is an important one. These are all measurements of the quality of that as a solvent. We're not going to fool with those, but it does show you that there is a fair amount of overlap. So to come back to polarity a little bit more, particularly in the ways that we're going to alter polarity, we're more likely to do it with changing ratios of alcohol, ethanol to water, maybe the addition of glycerin, maybe some of these other solvents that we've talked about. But polarity comes down to like dissolving like. And we're talking about, in polarity, oftentimes you are looking at charges on a molecule. So you can begin to look at, and when you begin to understand some of these molecular structures and what's hanging off of them, you'll be able to look and say, oh, okay, that looks like something that would dissolve in water, or maybe this actually requires more ethanol. And just go through and think about some of these herbs and the likelihood that what you're pulling out is either very low ethanol, which means it tends to like water, it's very soluble in water, versus high. And there, think about something like cayenne. Cayenne is a pepper that heat element, that capsicum has a real oil-like quality to it. Whereas something like golden seal, these are the alkaloids in there, they just don't tend to come out in water very well, so it needs that high alcohol content to pull out the alkaloids. So this is something worth looking over and beginning to study and think about. A fun game to do for yourself is to pick one of these herbs out of each column. Go find the active components and compare them terms of what you might understand about polarity, like the ginsenosides in ginseng. They tend to have a lot of sugars, so a lot of glycosides tend to be very water soluble. Thus, you would have a low 20 to 30% ethanol content there. And then you might go in and look at something like chamomile, 50 to 60%. Even if you take a chamomile flower and you crush it, you can get some of that yellow pigment. And pigments tend to have a more oily quality. And just play that a little bit, play that game to figure out. Grindelia has resins, so resins are going to tend to like higher alcohol content. So a case for using glycerin. Hydroalcohol actually can be a very unstable environment for some compounds because it tends toward the more polar end. Polarity tends to refer to reactivity to some extent. The same elements like oxygens, nitrogens, certain chemical, what we refer to as R groups, sort of functional groups that hang off the parent molecule. If they're reactive, they tend to be more polar. So sometimes you want to add a bit of glycerin in with some compounds that maybe you can point to that you're losing, either through organoleptic analysis or some sort of analytical approach, because the polarity comparisons are water being the most polar, alcohol intermediate, and glycerin much less polar. And also you get some very strong differences in pH. So in alcohol, you tend to have ethanol a pH of around 3, glycerin 7. So you can play a little bit using those solvents in terms of altering your pH. And you can either have separate extracts, one each of hydroalcohol and glycerin, and then mix them together, or the glycerin can be added after the fact to either alter the pH to sustain the molecular structure or to alter flavor. And that's something that Bevan's going to be pulling up in the rest of the class, looking at some of the elements of compliance around how things taste. Also, glycerin does tend to draw water to itself. It's considered hygroscopic. Now, we did mention pH, and particularly with the alkaloids, this is something that becomes important because you actually, the term is to protonate a tertiary amine. A tertiary meaning there are 3 bonds that end up at the nitrogen. You can have quaternary alkaloids as well, where you actually have 4 bonds. And I would suggest when we get to the section at some point on discussing golden seal and those images of the molecules come back, think back to this terminology and what it might mean. Because a lot of what you're doing is you're getting new terminology here. And the terminology either describes something that you already know, and now you can link it to that old information, or what it does is it really introduces you to new kinds of thinking. The pH also later on will fool with elderberry and changing the pH in terms of extracting the pigments, and the pigments largely are anthocyanins. And as I mentioned, the glycoside, the sugar molecule, needs to be attached to the parent anthocyanin to have these elderberry compounds active. So if you get it where it is too much on the basic side, you might actually begin to lose those compounds and not have an active extract. So that would be something to think about when you're doing an extract for elderberry. And here's some basic, I wouldn't know if I'd say basic, but these are things you can find around the house. As I mentioned, we're going to use baking soda, and we're going to use white vinegar, not white wine vinegar. The white vinegar is largely acetic acid, very mild. But even with lemon juice, you can drop a pH down pretty low using things that you have in the kitchen, as well as trying to raise it. It's a lot harder to get your pH very high. You tend to have to go to things that are pretty toxic, but we can use baking soda solutions. Now, a couple of interesting specialized extracts by mixing various polarities. If you include glycerin in an extracting menstruum, that liquid, For tannins, the glycerin will actually bind to and exclude the tannins from your extraction. So there are uses for tannins, and tannins are in a lot of plant material, but they either can give a very strong flavor, or they can have a very, if you can think about wine or some compounds like that, where you get a green tea where you're sucking on your cheeks, right? Those are the tannins at work. You can also precipitate it out with table salt and gelatin. And you can also go the other way. You can choose for tannins. There are times you want tannins for certain conditions, and you can get a great tannin tincture by using 20% alcohol, 80% water. Other things to think about, and this is from an interesting site, the Herbarium WordPress site. There are certain plants that you're going to want to extract fresh and succulent. So shepherd's purse, corn silk, even echinacea. You'll find a lot of good herbalists that say they will not make an echinacea tincture from dried material. You can have extractions after the herb is dried, so the hops and the grandelia actually are better. You get a lot of the water content out. You don't get some of the interference that you'd have in terms of trying to pull out the more lipophilic compounds in those two plants. Semi-dried in the saw palmetto. Some plants will require actual fermentation, like the wild cherry or sweet clover. And think about that. What is it that fermentation would do, right? Fermentation is really an enzymatic process. And in this case, what's really happening is that the glycosides are getting cut in this case to activate, to create, take a pro molecule and turn it into an active agent in the body. And then others where you have to dry for a much longer period of time, like buckthorn or Cascara sagrada. And then finally, we're going to look at two methods for extracting the full range of plant compounds. Now the first one, if you look at those bottles, this is on the bench top. This is something a natural products chemist might do. And what you're seeing in the boxes, I know it's hard to read, but this is a form of an extraction protocol where you're asking either or questions. So if you go to the third box down, it's an aqueous methanol extract, and you're going to mix it with hexane. Well, you're going to have a very polar solvent, and then you're going to introduce a very lipophilic solvent, and you're going to get two very different fractions. And what you'll end up having, actually, to some extent, is you might actually have to shake up an extraction like you do oil and vinegar to create a salad dressing, and then if you let it sit, it separates. Well, they'll do that. They'll get a lot of surface contact between the two solvents, let them sit, and then they'll pour off one over the other, and they'll contain different molecules in those different fractions. And then they might dry them down, that's where you see the term residue, and put in another solvent that will, again, either produce a precipitate, something that won't dissolve in it, and other compounds that solubilize or are actually extracted in that liquid. Now the problem is you're using a lot of harsh chemicals here when it comes to medicine making, and there's a lot of post-extraction purification to remove those solvents and get down to limits that are acceptable. Well, it's a lot of work, and I think there's some better ways to do that. And one of them is to look at contemporary technology. I know as herbalists sometimes we think the traditions figured everything out, and one of the strengths of our program, in my mind, is that we try to use both because we feel like there are contributions and there's knowledge to be had from both. Now, supercritical extraction refers to the process of a supercritical fluid. And if you look carefully at this on the bottom, you have from the left to right increasing temperature, and on the vertical axis you have pressure starting at the bottom going to the top, low to high. And at some point when you take a gas and you put it under both pressure and temperature, it will literally turn into a supercritical fluid, something that is both gas and liquid in its properties. This is what it looks like You might have a CO2 storage tank. There would be a compressor. Here's your pressure element, and your heat element. Now you create a supercritical fluid. You mix it with your plant material. It's extracted, and now you're literally separating it then. So you have your extract, and what remains is your supercritical CO2, which now goes into a condenser and ends up being turned back into gas form and recycles. So it's high recyclability. CO2 obviously is very inert. And there's some other benefits to it. The CO2 has a very high diffusion rate to penetrate material better than liquids. So that element we talked about getting into the cells to actually dissolve those compounds. It doesn't leave a residue. It can operate at temperatures lower than some expeller press organic solvent methods, so you don't lose compounds to heat breaking them apart. It has the added benefit of limiting the oxygen exposure because it displaces oxygen, and oxygen tends to be a reactive element in any extraction process. And it's better with lipid-soluble or low polarity compounds. And the nice thing is you can actually add co-solvents to it. You can add water, or you can add ethanol and really alter the spectrum. So you can run things through and then run things through a second time and begin to add increasing levels of ethanol or water and begin to change the polarity of the solvent so that you can pull out a full spectrum of the molecules that might be useful. So the last piece I just want to show you, because I think it's important, we're talking about solubilizing and then identifying molecules in an extraction process. Well, how do we know they're there? We have detection. We'll talk a little bit more in another lecture about coffee and organoleptic analysis, and that it can be very useful. Although the FDA does not acknowledge organoleptic analysis for metabolite profiling, they do allow it in some instances and in combination with other methods for identification of a plant, but not its chemical makeup. So we tend to have to learn some other methods. The one you're seeing there is a form of what we call paper chromatography, or TLC is another one that we refer to it as well. And this is really a form of a stationary phase, which is it's a silica, in this case, that's been spread on a thin layer on glass. You've got a marker that has black ink. You make a spot at the bottom and you let it dry, and that whole apparatus then is the stationary phase, and it's put in water or some other solvent, which is the mobile phase. And what happens is that the solvent tends to get wicked up that material. It literally climbs, and you tend to get reactions in terms of both the solubility, how much of that solvent is needed, and how much it interacts with the solid that it's sitting on. And so some compounds, like the blue in this case, isn't as soluble in the solvent and tends to like to interact with the silica on that TLC plate, whereas the yellow, in this instance, is highly soluble in the solvent and tends to get carried much further. And this is how we get a separation. In the same sense, we use high pressure liquid chromatography, which has a column and a liquid under pressure running through it. This is an example where they are comparing two different elderberries, Sambucus canadensis, which is used in trade, and Sambucus nigra. And these are both the anthocyanins and the polyphenolics. It's the European, the nigra, that's used in trade. And you can see they're very different. They have some similarities. So if we look just at the polyphenolics, we can see that 1, 2, and 3 are very similar, as are 4 and 5. But where we get a real differentiation, and this could be both for speciation, being able to identify a species, but as important for its medical activity, potential either toxicity or safety concerns or efficacy concerns. You can see in the canadensis the 6, 7, and 8 are very different. The anthocyanins are even more different when we compare the two, and you can see that the high levels of 1 and 12 and 13 are, in this case, anthocyanins that we aren't apparently as useful, because they've compared, some trials have compared American elderberry versus the Niagara, and they see greater activity in the European version. So that's the lecture, really looking at how we dissolve things, how we select for them in a rational manner, how we can begin to look at some of the chemical profiles and begin to use that as a selection agent. We can use a number of ways, from HPLC to TLC to organolepsis, to decide for ourselves what's happening. Pick up a glycerin extract of echinacea versus a hydroalcohol and see if you don't taste a big difference in the buzz on the lips and tongue that are the isobutylamides that come out in a higher alcohol content. So this is just the beginning. As we begin to think about making rational choices, this is some information to help us do that. Thank you. I appreciate your time.